All right, folks, welcome back. I would like to start with the topic for today. The topic for today is MLOps. Now, ML flow. Within the world of MLOps, it has quite a significant place, and I will sort of walk through the some basic overview of it. See, when you do a machine learning project, it's quite a long journey. In that journey, so far you have been doing the pipelines. For example, you have Jenkins or Kubeflow and Flight and so forth. These provide you a process orchestration backbone. While that is a core part, it's a necessary part of the MLOps, it is not sufficient. The ecosystem that makes up ML is wider than that, broader than that. We need to do a lot of things that we haven't, like, for example, you take in data, data comes raw. Now, you do a lot of transformations on the data and you do feature extraction. As you do feature extraction, you have burned through a lot of compute, a lot of effort, a lot of data engineers have worked at creating that data pipeline. Through all those data wrangling, through all those transformations, when you produce the features, quite often, features are closely tied to specific machine learning algorithms. But quite often, the features are shared between machine learning algorithms. When you have created features, it is an asset. It has a life of its own because another data scientist can come by and say, hey, I want to build a model, and these are some of the features I need. Do you happen to have these features? For me, for my use case, I need these features. So in other words, can you have a buffet? Can you have a marketplace or a repository of features into which data scientists can with ease dip and go and take the features they want? And ideally, they shouldn't have to reinvent the wheel. They should not have to start with features from first principles, from raw data. It is a no-brainer. So you need a way to manage and save the features. Such things are called feature stores. We will be covering feature stores in a subsequent session. It's very important. But more importantly, as you move forward, you train a model. Let's say that you train a particular model. For example, in your case, you have been working so far with California dataset and breast cancer dataset, but now you'll be working with generative AI with LLM. So you'll be doing RAG and sentence encoding and so on and so forth shortly. In all of these situations, let us say that you're training a model. The first thing you do is you extract a data set of features. So you need to, and you train the model. The moment you train a model, multiple things come out of it. First, given a model, you need to remember what data set it was trained on. So you need to preserve, you need to freeze exactly that version of a data set somewhere, of that feature somewhere. Another reason these frameworks come in useful, you should be able to store that, right? Not only that, you need to have a version of the model. The model will have lots of hyperparameters. So if you're looking at random forest, which is made up of trees, a basic question is, how many trees are there in your random forest? How deep are those trees? Like, are you letting the trees be shallow, or are you letting them be deep? What is the level of parallelism that your training is supporting? Like, as you train the machines, you may have certain number of cores, certain number of hardware available. These days, the number of cores on CPU itself is gone up phenomenally. For example, in the back room in the data center, then Epic has, from what I know, 128 cores. right? Or another one has 96 cores. So that brings the question, if you're passing data through trees, each of them individually can be trained in a forest, random forest. Given your hardware, what's the level of parallelism that is optimal to run in training your model in which you can finish in the shortest amount of time? So on and so forth. There are many hyperparameters that are associated with model metrics. There are some hyperparameters which are sort of about the hardware and getting efficient utilization. So let us say that you succeeded in doing this and you did a hyperparameter search. Now, hyperparameter search itself is a complicated topic. In how many ways can you find the best hyperparameters? We are often taught to do grid search, right? So suppose there are two hyperparameters, take 10 values on one hyperparameter, 10 values in the other hyperparameter. And now for every combination of parameter A and hyperparameter A and hyperparameter B, now you build a model and now you compare those 100 models and see which one is best. That's the way typically you're told to do hyperparameter tuning. Now, so one question that often comes up is, why do we need to do hyperparameter tuning? Won't the machine learning model itself figure out the best hyperparameters? The answer is yes and no. The model training only tunes the parameters of the model, never the hyperparameters. So for example, if you have a neural network, the, the process of training the model leads to the process of gradient descent and backpropagation is only going to leave you with a set of optimal weights. But those weights and the performance of the model is still contingent on a bunch of things called hyperparameters, which you can't do through gradient descent. So these hyperparameters, for example, in the case of a neural network would be how many layers of nodes, how many layers you have in a feed-forward network, how many nodes are there in each of the layers, what's your dropout rate, what is the level of regularization, what is your learning rate or learning schedule that you're using. Now, it turns out that for each of these hyperparameters, combination of hyperparameters, you will end up with a model with a different performance characteristic. In some cases, like in the case of just a feed-forward network in which you don't know how many layers you have, how many nodes per layer, etc., it becomes a specialized field that is called neural architecture search. Right? So it's a form of hyperparameter tuning. You're saying, what should be the shape of my neural network? How should it look to produce the best performance of the given task for the use case? And so you need to keep track of all these hyperparameters. By the way, I started by saying grid search. I must also say, while it's the most prevalent form mentioned on the web and in the textbooks, it is, in my opinion, also the most impractical and useless form of hyperparameter tuning. Because as the number of hyperparameters increase, as they do in contemporary networks, contemporary AI models, the number of hyperparameters are not one or two. They are dozens, if not hundreds. And so you cannot do grid search, or an improvement on grid search is randomized search. It doesn't work. What you need is an entire field of a subfield of machine learning, which is called Bayesian optimization. You need to bring in Bayesian optimization methods to do hyperparameter tuning or finding the best hyperparameters. Here is the core intuition behind a Bayesian optimization. Bayesian optimization takes an approach. It says we cannot obviously do gradient descent, but what we can do is do uh, a sense of the Bayesian inference has a bit of mathematics, but basically it says that if I have tested out this situation, this bunch of hyperparameters and that bunch of hyperparameters, what is the next best combination of hyperparameters to try? Where am I most likely to get better results? Right? So that's a Bayesian conditioning on it. Condition on what I've tried so far. What is the best combination I should go for next to try out? Right? Now, in some sense, those of you who are familiar with Markov chain Monte Carlo and Gibbs sampling, that is how, or the Metropolis algorithm, you get some sense of a flavor of how Bayesian optimization methods work. But those are the right approaches to apply to hyperparameter tuning. So you need a framework that supports hyperparameter tuning using the state-of-the-art Bayesian methods. Many open source libraries have come up to do hyperparameter tuning, OpTuner, HyperOpt, and so on and so forth. So the question therefore becomes, does your um, complete machine learning lifecycle management system have support for those? Now, let us say that you do find the best hyperparameters. Now you have many things to store about a model. You need to remember what data set you took. You need to remember the test train split. What was the training data? What is the validation data? Right? The test data. You need to remember the best hyperparameters. You need to hopefully also remember how much effort was put into finding those hyperparameters. You need a system that will systematically do multiple runs of the training and find the best hyperparameters using the state-of-the-art hyperparameter search methods. You need something for all of that. You also need to version the model, because tomorrow a different kind of data may come in. You may, even with the same hyperparameters, you may have to retrain the model because you experience, well, if the data has experienced distributional drift, then your model won't work. Like, for example, the weather models of today, um, as you know, they're going through a crisis because the climate has been changing so fast that years of historic data on weather is not proving, and the models based on those are not proving as effective as they used to be. Now we are going through an accelerated and what may be a catastrophic um, change, rate of change of weather, which means you need to you need model retraining all the time. So you need to therefore have a whole model management framework, data versioning framework. Lastly, all of these things is important, but soon you get lost in this zoo of things that you have to manage. You need some visual dashboard, some way, for example, to keep track that the model that I built today is better than the model from last week. Otherwise, there would be no use, no point in taking it to production, isn't it? So you need to have some way to some test data, and you have to have ways to compare the results of various experiments, various models that you build, and see that yes, your models are improving day by day, right? And again, in your deployment pipeline, you need to have some guarantees that you are taking a superior model to production from the dev environment, right? Otherwise, there should be automated blocking factors that prevent your model from going to production. There should also be frameworks to check for adverse impact, especially if you work in domains like HR. At one time, I used to work for in that domain, and it's very, very important if you make decisions, for example, about hiring people or even recommending which resumes a recruiter should look at. You need to be extraordinarily careful that you don't introduce what is called adverse impact or bias. In US, that's the law. There are these protected categories: gender, race, age, etc., etc. And if it is proven that your model inadvertently creates such bias, you are legally liable. You cannot say that there's no factor that you introduced, no feature that you introduced in the training of your model, no data it was trained on that could imply the age, because these machines are extraordinarily clever, and they may find latent patterns in the data. And sometimes those patterns in the data may imply one of these protected categories. So, for example, two cases worth mentioning in this and which is why monitoring the model and checking it for these validations is very important. Long ago, there was a company, I believe, named Kronos, which got sued because they were using algorithms, neural networks, to recommend who to hire and who not to hire. Till candidates sued that it is discriminating on the basis of race and gender. I believe those were the two categories. The defense was we were not feeding data of any of that kind into the neural network, but they lost the case simply because the fact is whether or not they were feeding such data, the model was discriminating, and it is the law that you cannot discriminate. It was the job of the company to do an adverse impact analysis, which they had not done. A similar thing happened with Amazon much more recently. They tried to create algorithmic hiring of the candidate. You guys know the history. They had to take the algorithm back because it was preferentially picking up men, right? And so on and so forth. So you have to have safeguards, and you need to keep track of that data, because tomorrow, if there is a legal challenge, you need to be able to produce the evidence that at least you did due diligence to prevent these things. See, you can never avoid it, but what the law would like to see is that you have done due diligence. Likewise, your management would like to know that you have done due diligence to prevent attacks. These days, we use generative AI, prompts, and prompt hacking. Prompt injection attacks are very common. Data poisoning is very common. One of the easiest ways to get a model into trouble is simply to inject malicious data. Now, you would say, how can somebody from outside inject malicious data? Herein comes the fact that most attacks are not from outside. Most attacks on AI systems almost always start from within. Disgruntled employees either deliberately do it, or careless employees do something that has some impact, which has some other impact, which basically creates trouble without their realizing it. So between negligence or incompetence and malice, a lot of the attacks come from within. So data poisoning can happen. Who is safeguarding the data? What's your data governance policy? Goes back again to your feature store. If you're maintaining a feature store, somebody has to safeguard the feature store and make sure that your feature store is not poisoned in any way, right? And this is very serious, by the way. People have shown long ago, actually, that, for example, more than a decade or two ago, it was shown that, for example, support vector machines could be poisoned with very little data. All you had to do is make the support vector machines algorithm pick the wrong support vectors to make the decision boundary. Then it becomes a no-brainer. In fact, every single algorithm that you can think of can be poisoned and taken down with malicious data. So, and judicious injection of malicious data that you don't notice. When you have such a complex system, one of the first things that you have is how well is the system supporting collaboration? Because no one person is doing everything. There are data engineers involved, there are AI researchers involved building models. There are people who are doing data governance. There are people doing they are doing model security. There are security teams that are looking for SOC 1, SOC 2 compliance. There are, and if you're dealing with US government data, FedRAMP, there are people all along the journey. There are ops people, like as in you guys, who are going to take care of the deployment pipeline, who need to rest assured that there is an easy way to collaborate with all the upstream people, the data scientists, the data engineers, and everybody, to for them to certify a model in a defensible way, so that you can pick it up from a model repository and take it to production. In this course, you will be using Ray framework. So the question comes, you want to do Ray inference. How would you pick a model programmatically from this whole ecosystem and deploy it? How can you do, for example, blue-green deployments? How can you do automated deployments? Right? Continuous integration and continuous delivery. Right? So CI/CD, by the way, in this world of AI, we don't use the word CI/CD so much. We actually use the word CT/CD. What could CT stand for? Would somebody like to guess? Anyone? Well,
Continuous trials.
continuous training, continuous training, close, continuous training, because you always believe that the models should be continually trained. I'll give you an example. These days, for example, when you train a large transformer model, language model, you are fighting competing pressures. The pressures that you are facing is time. You need to get to market as soon as possible. At the same time, data is accumulating. And as more data accumulates, you would like to continue to train the model more and more. Then there are other things that we have observed. The more tokens you train it on, the better the model. There's the neural scaling law. You have a model, even if you don't make the model bigger, the longer you train the model on the same data, the better it gets. Indeed, we have now found things like grokking, which means that all of a sudden there's a phase change and a moment like grokking happens in which the model suddenly becomes literally in its performance way, way, way better than it was prior to the grokking movement. Well, that is one sort of a remarkable phenomenon, but even otherwise, there's a progressive improvement in performance of a model. The more you train it, the more computes you put at it. That's the neural scaling law. The second part of the scaling law is the more data you train it on, the larger data set size, the better gets your model. And of course, the third is the bigger you make the model, the more, the better it gets. So you could be moving along all three axes, except that time is of the essence. You have limited hardware, you need to get to market. So what you typically do is you train a model and you keep checkpointing it. And at each checkpoint, you're observing the model metrics. So you need a dashboard to be looking at the model metrics. For example, you could be testing against a whole bunch of inputs and seeing how well it does, right? Then, when it reaches an acceptable limit that you can take to production, you take that checkpoint to production. But does just because that checkpoint has gone to production is no reason why the model should stop being trained. This is essential, by the way, because there are many downstream tasks. You may be doing the you may be doing the adverse impact, the responsible AI exercises with a checkpoint way before you have done training the model fully, right? So you don't stop the downstream work. A lot of work has to continue and happen as you train the model. And so your model actually, given a certain amount of hardware for training, quite often you just go on training the model with more and more data, with more and more, of course, compute cycles, right? You do that. And occasionally, of course, you replace it with more sophisticated models. So we have entered the world, just like in the world of software, software keeps growing. We have entered the world in AI, in machine learning, of continuous training. So as you continuously train, this is the new reality. Continuous deliveries of the checkpoints. Is it making sense, guys? Right? So for example, today, if you were to ask, should I, the Llama 3.1, the big model, the hundreds of parameter model, what does it represent? Does it represent a point at which the performance reached an asymptotic limit and you couldn't improve performance? By no means. You could continue doing it. It's just that when you train it on, and as you saw in the presentation just a little while ago, it was trained on 24,000 machines. Right? When you train it on 24,000 machines, you realize that you're burning enough electricity to power a small town. And you are burning through a massive amount of money, resources, compute resources. So you have a choice to make at that point. At what point is your model state of the art? And worth releasing. It doesn't mean that you can't keep on improving the model, but at what point you want to free up the resources to build the next, to start training the next model. Are we together? So you can have incremental improvements to the current model, or you could just free up the hardware and start building the next model. These are real trade-offs you face on a daily basis. Well, that is for hyperscalers. You and I, it turns out we have a little bit less than 24,000 GPUs. So what can we do? Right? What we can do, our reality is no different. Let us take a hypothetical situation. Let's say that you have a bank of 8 GPUs, like for example, we have here. You start training a model, you take a model, you start training it. While that model is continually getting trained and improving and more data is coming in, you take a checkpoint, that is good enough because you need to now change the data set entirely. You take that checkpoint and you create multiple versions of that model. One model you fine tune for one use case, another model you fine tune for another use case, another model you fine tune for another use case. And you may be doing it through LoRa, through a perf and LoRa adapters, and you're busy training a whole lot of LoRa adapters and then using merge kit to merge all of them. So the real life activity that you face when you do machine learning, or when you do machine learning at this scale, even at the scale of a startup as we are, is that there are many, many models that you have to build on essentially the same hardware, right? One group of hardware. And before you know it, because especially with this world of fine tuning, you have multiple choices. Are you fine tuning with the whole models unfreezed, all the weights unfrozen? Dangerous because it can have catastrophic forgetting. Are you fine tuning with some of the layers unfrozen, later layers unfrozen? Are you fine tuning with all the weights frozen but using some form of uh, PEFT, performance efficient fine tuning, things like LoRa, etc.? And we'll cover LoRa fine tuning in this course. You'll do those exercises. So actually, I take that back. It is a sequel to this. We pushed it out into the fine tuning course, and you'll be doing all of that there. So as you do this, the question comes, how how do you manage all of that? You need a systematic framework to manage all of that. So that has arisen as many, many contenders have come about which help you do that. And so here is a small list. The oldest of them, perhaps, that got a lot of attention, um, for Kubeflow, for example, is quite dominant and used in the enterprise. Its dashboarding is good, though I wouldn't call it excellent. Right? It's not that intuitive. But then there are people like Weights and Biases. It's a website, it's a commercial service. They do give you free use for development purposes. So many of you may be using Weights and Biases. If you're not using, use it. Another one is Neptune, I believe, for development, for basic development or academic use, learning use, it's free. There is TensorBoard. TensorBoard is, of course, absolutely free. It comes with PyTorch and with TensorFlow. It came out of TensorFlow, but now you can use it for any framework. Comet. Comet is another. Now, these are commercial offerings, Weights and Biases, Neptune, and Comet. And there are different pricing strategies. Generally, it's easy, like in the beginning, if you're a small startup, the prices are not that much. But once you have lots and lots of models that you're training, you might get an unpleasant surprise. You have to keep your eye on that. And nevertheless, they're very good frameworks. They're very intuitive frameworks, and you can use. Now, that kind of ease and intuition does come with a price. You have to look for a good compromise, something that, for example, Qflow is very powerful, but it doesn't give you perhaps as rich and as intuitive an observability as, let's say, Neptune or Weights and Bias or Comet would give you, right? But there's a middle ground that you can take. And we considered the middle ground to be MLflow. It's an open source project. Amongst the open source projects, it is quite intuitive, reasonably well done dashboard. And today we'll walk you through a bit of it, and subsequently, Chanda is going to continue this in the session on Wednesday, and he'll walk you through the code. You'll do it, and you will have a homework, guys. Now, I would strongly encourage you to take MLflow seriously. You need one ecosystem, one lifecycle management framework. If you know MLflow, the others are not different. You can pick up the others. They are very similar. You have already done Kubeflow, but MLflow has a lot of mind share. It came out of Databricks, same guys who created Spark, right? And they have done a pretty good job of it. Um, it has very good integrations with a lot of things. So here is a matrix that shows how well these frameworks are doing with respect to, this is a comparison matrix. Let's look at it. How well can you do experiment tracking? MLflow, yes, you
As
can
if you're
do.
not sharing.
Oh, I'm not sharing.
Yeah.
Good, great. Okay, let me go and try an attempt at sharing now. Okay. So I mentioned that there are all these frameworks, MLflow, which we put as number one, because we felt that it was a good compromise between being very intuitive and expensive and being, on the other hand, very powerful, but perhaps a little bit intimidating as Kubeflow can be, right? So use Kubeflow for deployment, for pipeline, as you have done, but nevertheless, it helps to have a little bit more intuitive observability and so on and so features, or at least when you're starting out. So we thought MLflow was good. Weights and biases, Neptune and Comet are the commercial offerings. TensorBoard is basic. It just gives you basic observability. And you don't get all the things that you expect from a full lifecycle management stack. So let's compare these things. Let's compare MLflow, weights and biases, Neptune, TensorBoard, Comet. By the way, this is not to disparage. One second. This is not to disparage all the other frameworks that we have not covered. Right? There are many. So if you don't find your favorite ones here, it is either our omission, inadvertent omission, because we have to take only a few, or our ignorance. We may not be aware of it. So you can educate us on any nice new framework that came up. They're coming up very fast and hard to keep up. This field is exploding. If you know something better, educate us. Yeah, somebody is saying something?
Uh, Asif, this is Albert.
Yes.
So Asif, is this all these frameworks, are they for any model or just LLMs or?
No, they're for anything. In fact, we'll deliberately show you that these frameworks span all of machine learning. See, we use the word ML lifecycle frameworks deliberately. We didn't say LLM lifecycle management framework, right? Or neural network management framework. Yeah.
So second question is, do we need a framework for a simple model? Right, then it becomes complicated to kind of manage that, right? So
here's the reality. Let's take a simple thing. Let us say you're Zillow, right?
Yeah.
And you're trying to predict house prices, of which California housing data and the Airbnb data are sort of baby examples. First, let us say that for whatever reason you choose to use only one model, the random forest that we used. Right? Now, look at the reality. You will not have one instance of the trained model. Algorithm is one, random forest. But how many models will you have out of it? Many, because real estate data is flowing in continually, isn't it? Houses are being bought and sold every day. And they are valuable data on which your model should be continually retrained. Hyperparameter search induces you to, again, have many, many models from the same algorithm. For example, how many trees do you want to grow? Do you want shallow trees, deep trees? Because random forest has a tendency to overfit, right? It has variance errors, right? Not as much as a decision tree. Nevertheless, it does have worrisome amounts of variance errors. What are you doing to prevent that? Right? So on and so forth. So all of those hyperparameters ultimately lead to an explosion of um, models. One algorithm, same code, run over and over again. Remember, we use the word continuous training. How will you manage it? If you think about it, Albert, you'll have to start creating directory structures by date. Then within that, you'll have to start doing hyperparameters, different hyperparameter values. You'll have to start doing all of that. You see that, right? And soon you realize that you're creating a mini lifecycle management framework of your own, isn't it?
Thank you.
And so it is worth, these frameworks are easy to learn. The learning curve is low. I mean, the learning curve is different for different ones, but generally they're fairly manageable. And if you are in MLOps, I mean, you like if you're taking this course, inevitably, you will be the team that's to which data scientists, different data, like, how did I position this team? Six groups of data scientists have approached you with six different use cases or seven different use cases, and they want you to go to production. They will not bother about versioning and lifecycle management. It is your bother. So you need to have a tool to do that, because even if a model is too simple, and you might want to do it with files, for the other teams, you're doing it with using these tools. So why not do it even for the simple cases in one place? So there's a single dashboard over everybody's models. Any more questions, guys? Let's continue the comparison. It's a good comparison. Um, so experiment tracking. Every experiment, you need to worry about hyperparameters, metrics. What are the artifacts that came out of it? Like what was the test date? What was the training data? And so on and so forth, right? What checkpoints you took, everything. So MLflow has support for it. Weights and bias has extensive tracking and visualization. By the way, let me open up weights and biases and MLflow and all of that. WANB, this side. By the way, again, this for simple use, it's free. So play with it. In fact, I will request that all of you, one of the homeworks labs will create is, and Chanda, can you please take people at some point, doesn't have to be this week, through a little experience with weights and biases and Neptune and Comet. These three are key ones. They have very intuitive dashboards. Somewhere in the course, we should do that.
Yeah, we can do it next week actually. Maybe because this week is planned to MLflow.
Yeah, definitely, definitely. So, guys, I'll give you an idea of WAND, why WAND was so popular. See, what you do is you say import WANDB, run with a project name, and after that, you just give some configurations and you run your model. What are the pluses and minuses? First of all, you get locked into WAND, the weights and biases way of running your models. Right? So it does put some constraint onto you. But what are the pluses? The pluses are you get a beautiful dashboard. If you go and look at it somewhere here, you will get a developer guide, a tutorial, uh, track experiments. You will get something like this. Do you see how rich it is, visually pleasing? Actually, MLflow that we are going to do today also has such dashboards, but perhaps may not be fully as polished, though it is getting there slowly. So I talked about hyperparameter optimization. Do you see that, guys, here? There are different hyperparameters. This is a parallel access visualization, and it is searching through. But one interesting thing that it is searching through, and this particular thing must have used some form of Bayesian optimization. Do you notice that in some places, here, for example, it searches only two around only two values of the hyperparameter, right? And that is one of the lessons, that you do want to use a clever technique that doesn't try out every single grid search across every single potential value. That would be catastrophically expensive. Right? So anyway, going back to it, weights and bias is very easy to incorporate. You can visualize the predictions, etc., etc. Like, it gives you all of these things. Yeah, this is it. A hyperparameter search and this and that. And you can do all sorts of things. But it gives you model tracking, track models and data sets. Right? And everything is very visual. I suppose that's what they're charging you for. They make it intuitive, visual, and make it easy for you to work with. Then there is Comet. And again, I'll just mention Comet. Do you notice that there is a sense, this looks very familiar? Oh, there is literally California house regression. I didn't realize that. Yeah. Well, California housing dataset has become sort of the hello world, and it has this. It's a 3-minute video, but I won't do that. I'll just jump. I will just jump to places to show that you can do it. And you will see that ML flow that we are going to take you through, all of these interfaces are more or less within the same ballpark, right? Then you have Neptune. And once again, they have a couple of a demo. Maybe it's a 2-minute demo, shorter demo. We can watch it.
Training foundational models can take months and cost millions of dollars. You run many experiments, constantly reviewing the results. You train on highly distributed infrastructure where failures happen, causing anomalies that you need to spot swiftly. The goal is to release the next better, more scalable, and more robust model. So you need to iterate fast. Instead of waiting for this next chart to load, opt for an experiment tracker that will keep up with the scale and speed. With Neptune, you can track and analyze multi-month training with no workarounds. Restart a failed training session or branch into a new training configuration by forking a new run from any step. The training history is inherited, and you can visualize the whole tree of run branches on one chart out of the box. No matter how big this tree is, the web app remains snappy and responsive. The forking capability ensures accurate results, no matter how many times something goes wrong during training. It also allows for testing different approaches without starting from scratch and duplicating the GPU usage. Neptune can handle hyperscale. It can log hundreds of thousands of runs, each with over 50,000 metrics and over 1 million steps per metric, and display them effortlessly without worrying about app performance. The runs table still renders extremely fast. Rendering huge comparison charts takes milliseconds to 5 seconds at most, so you can explore the results in a blink of an eye. And what's more, the results are 100% accurate. Even a single outlier will be displayed accurately on the chart. Yeah, we're talking about you, little guy. Neptune can ingest 100,000 data points per second and ensures reliable asynchronous data ingestion based on Kafka. And it's ready to be deployed on your infrastructure from day one. Don't let your tooling slow you down on the way to the next AI breakthrough. Use an experiment tracker that's ready for the challenges your company faces. Use Neptune, the most scalable experiment tracker on the market.
All right. Pretty convincing argument that you should use Neptune. Why would you not use Neptune? Would somebody like to venture a guess? Anyone? Guys, it's vendor lock-in. After you set up on this, you better be sure that you're willing to pay the bills, right? And their bills are not. Let's go look at the pricing, and you'll realize that, look at this. It's pretty, I mean, if you have a team of 100 data scientists, you're paying huge amount of money every single month. And there, like, enterprise pricing is there. Likewise, Comet has a pricing, I'm sure, somewhere, pricing, right? Oh, everybody seems to have gravitated to $50 a month, right? WAN-DB, let's look at their pricing if they have advertised their pricing. They must have.
I think MLflow also, if you go through Databricks on a hosted platform, it is.
They charge you. They charge you. That's true. So they have a cloud-based, if you use the cloud, you pay, but they allow you to use it in-house, right?
Yeah.
That's the thing. So here we go. So cloud, privately hosted, right? Personal use, free. Right? In the beginning, stick with that. Right? And
Asif, how
enterprise
about
use.
Kubeflow?
Oh, Kubeflow is very good. That's what I was saying. The trade-off is, see, Kubeflow is both a pipeline as well as a full, it's a big
Actually, Kubeflow is
ecosystem.
a whole suite. It has many things in it. So, and it's native to Kubernetes cluster, right? So there is a steeper learning curve to Kubeflow.
Yeah, and it's open source, right?
Yes, it is open source. See, just to emphasize what Chandra said, I mentioned that there's a continuum between very intuitive, right? And not so intuitive, but extremely powerful. I would put Kubeflow on the very, very powerful side. It's a bear of it. But try to set up Kubeflow in an enterprise environment, like do an enterprise deployment. And you would need a team, an MLOps team to be able to do it. You need to get your Kubernetes right. You need to get your cluster right. You need to then have Kubeflow. And it has many, many components. And all of those components have to actually work properly. But when they do work, and most of the large enterprises, they do use Kubeflow. Nevertheless, recent trend has been, while they use Kubeflow, they often supplement it with one of these more intuitive things on top of it. Right? It's hard to tell because everything is competing with everything. Now Kubeflow is beginning to also develop lots of dashboards and so on and so forth. So check it out. In fact, I would not claim that I'm up to the latest with Kubeflow. With the last I played with Kubeflow, oh gosh, on the intuitiveness score, I wouldn't give them very high marks.
Asif, the clients, the customers going towards GCP are actually relying more on Kubeflow because it's Google.
And we did that too. When Chandra and I, we worked in a previous company, I used to lead the AI team, and I standardized on GCP. If you go to GCP, you realize that there is a MLOps team behind you. They have done the hard work. So you don't work on Kubernetes per se, you work on the Google Kubernetes engine. And in the Vertex AI, you get Kubeflow, in which all the kinks have been ironed out and it works flawlessly. So certainly there is a huge, if you're in GCP, it's a no-brainer to go with Kubeflow. I agree with you there. So, so anyway, let's look at other things. Model management. Yes, it has model management. They all have some degree of model management, except for TensorBoard, which is not really, it's just an observability platform. Model serving. Yes, you can do that. Though I would suggest that do not use MLflow for model serving. What should we use? What would I recommend to use? Ray. We'll be doing Ray framework, or Ray framework, or one of the NVIDIA offerings, Triton, and so forth, right? So then, of course, there's a vendor lock-in to NVIDIA. If you want to stay in an agnostic framework, then it would be the Ray serve. Data versioning is actually a little bit weak. You do get some data versioning support. It is evolving. Let's just say it is evolving. I would suggest use Feast or supplement it with something. Hyperparameter tuning. Now, if you look at the weights and biases, weight and bias gives you, as you can imagine, all the commercial ones give you a lot of data versioning. In fact, they would rather that you uploaded the data to their cloud, right? So, which you may not be comfortable doing. Then remember, guys, that data is king. At the end of the day, all of these companies, they are opening up their models. They're calling it open weights, but never the data. Next is hyperparameter tuning. This row has an error, actually. It says that Weights and biases, Neptune and Comet all have very good, they give you support for hyperparameter optimization using Bayesian, but MLflow doesn't. Actually, MLflow also does it now. It does give you Bayesian optimization. So in this area, this too is powerful. So this part is wrong actually. Visualization, yes, you have some graphs. Collaboration, that's the whole point of such frameworks. Integration with ML framework, etc. They all give you that. The CI/CD, though I would slightly change it to CT/CD. They all give you that. Deployments, yes. Ease of use, and this is where it is weaknesses. Remember, I told you that it's the middle ground between. And by the way, what I'm missing here is this one, the Kubeflow here. So if you look at Kubeflow, I wish I could present it in one big wide format, but let's look at the weakness to Kubeflow. Ease of use is medium, requires Kubernetes knowledge. MLflow, I would say, is a little bit easier than Kubeflow to learn, but still not as easy as these commercial offerings. Cloud support, of course, they'll all have. Right? Enterprise features, they'll all give you all of that, especially if you use the paid services. And here comes the kick. When it comes to open source, then both MLflow and Kubeflow are fully open source. Right? They're add-ons that they will charge. They all follow some sort of a freemium model. And cloud versions, of course, you have to pay for. Deployments you can do just about everywhere. So what are the key takeaways? MLflow is versatile and open source with strong features in model management, serving, and integration with multiple ML frameworks. Weights and biases, Excel. Notice the absence of the word feature store management. It's sort of weak here. Weights and biases, excels in experiment tracking, hyperparameter tuning, and visualization with a focus on user friendliness. Similarly for Neptune, TensorBoard is of course just an observability platform in some sense, or a basic visualization platform. Comet, Neptune, Weights and Bias, and Comet compete. Kubeflow is powerful for managing end-to-end ML workflows on Kubernetes. In fact, if you remember, you learned that Kubeflow as part of your pipelines. So it integrates just about everything. So with that there, I would like to just show you this in action.
Asif, one more thing real quick. ClearML, have you heard?
Oh, ClearML, yes, I have heard. Actually, thank you for pointing that out, ClearML.
We've heard from multiple customers asking for that.
Oh, okay. So let's add it to our repository, and let's add it to our notes. It's nice to know. Thank you for bringing it to our attention.
Okay.
Yeah. Arise is observability only, right? Mostly. Yeah. So we will cover Arise. Yeah. Arise is very much here. Arise is actually, there are a lot of meetups and things happening around Arise these days, right? Pretty hot. So this is it. It's an observability and evaluation platform. It doesn't give you the end-to-end service. But for observability, they're absolutely wonderful. So, all right, coming back, Chandra, could you give me the IP address of the...
Just a second. You cannot reach Grace Hopper, is it?
Yeah, I need the IP address.
Okay.
Or maybe I can find it out.
The 100 would be tail scale, right? 1 second.
No, ping. Okay, I can figure it out. Grace.
You can? Okay.
Okay, 221. And the port was?
8086.
86. So here we go, guys. After all this talk, what does it really look like? The MLflow. It's quite simple. Now, you might say that, oh, where is those wonderful, a splash of colors and so forth. So obviously there is
you can expand that plus sign on that.
Yeah, I will do that. Chandra,
yeah,
I will do that. Please. Sir. Yeah. So obviously it's an open source project. I think it's very well done, and it does have some little graphs, right? which we will go into slowly. So now let's go through this. There's only one experiment, California housing prices. Your job is to fill in the rest 5-6 cases with this. So do it, guys. I don't know how much because I'm not in the lab part. I'm not keeping track. I don't know how much you guys are doing the labs, but trust me, you're not going to learn much unless you do the labs. This is a given, guys. So let's look at this summary. First of all, the model was for California house prices. So there was one random forest model, right? And then, so where did this ape come by? What MLflow does is every time it tries another combination of hyperparameters, it gives it a mnemonic. It gives it a name that's easy to remember, right? So it's a basic practice so people can talk about it. Now, in this model, it gives you the basics like when was it done, run ID. You can add a tag, log model. So it says that you used a scikit-learn model. In particular, you use random forest. Now, what are the hyperparameters in the random forest that it came up with? But before we go there, let's look at the metric. In a regression, what would be some of the valuable metrics you would like to track? Default is mean squared error and R squared. Validation R squared. Val is for validation. Validation mean squared error and validation R squared. Right? So you can see that the mean squared error is pretty low and R squared is 83%, which is remarkably good. It's able to predict house prices quite well. Right? So if you feel like competing with Zillow, here you go. Right? Except that this was trained on data from 30 years ago, 25 years ago. Right? Now, when you talk of random forest, the question is, how many trees did you grow? That's a hyperparameter. And it came to the conclusion that the best number of trees were 1336. And number of jobs that you parallelized here, we chose 25, but partly because of the hardware, but actually because it's trained on a Grace Hopper, we could have actually gone much further. So one trick you can use actually is if you're using scikit-learn random forest, you can give n jobs is equal to -1. So it will inspect the hardware and pick up the right number of parallelism. System metrics, so artifacts, what things came out of it, right? So predictions, here is a bit of prediction, MLflow, predict on a data frame, etc., etc. Now, what are all the requirements? Like, do you notice that just about everything is available for you to look at? Which version of Python? Well, model you can't check because it's a pickle file under YAML, right? ML model, right? It remembers all of these things about the model. Now let's go back and see, well, what was it actually doing? If you open this plus symbol, you realize that, oh, do you see all this fancy name? Sincere Goose, I like that, right? Popular Rat and so forth. So all of these, it didn't do one run. It did many, many runs. And through all of these runs, which took different durations, it finally came back. At the top, it always mentions the best model. This is actually something.
You can use that columns, Asif, at the top, the columns to bring in.
The metrics also, yeah. The metrics, yes, good. And let's bring in the hyperparameters also. Okay, so guys, let's look at this. And we can hide some columns. For example, created, we can add model dataset, attribute dataset. Dataset we know is that. Source we actually know. Models we know. So let's stick to the measures that we care about. So you can see, if you look at this, if you take less number of parallelization, your training time goes up, right? So clearly, you need to have as much parallelization as possible. On this machine, actually, 25 parallelization is low because that machine sports more than 100 cores. So it could have easily gone to 100 to 200. So here, it is telling you that the best model was this, and this model ran with the best. But if you look, other ones are close by. They're not. It's not that they're very different. This is it. So this is a very good way. At this moment, Chinda, would you like to show something else? Should I hand it over to you?
No, we will be doing the lab in detail. So where we will walk them through the process of creating this experiment and also being able to register a model. I mean, in the first lab, we'll actually be walking them through this.
Okay, wonderful. So guys, look at this. The dashboarding capability is not bad, like a little bit usability maybe could be better. But what you can do is you can sort of expand it out, and now it is easier to see. So some of the best the model runs, it is telling you what was the MSE. Likewise, where are you getting the best R squared? They're all pretty close to each other. So this was a very simple data set, very simple experiment. Random Forest did a very good job. This problem has now become almost too trivial for modern AI algorithms. So all of them are giving pretty good values. But the thing to note is you can add more charts of your own, right? So for example, you could do parallel coordinates. The parameters are, you could add parameters, this, and you could also go and the metric that you pick is this. And you can see which of them is giving you the best MSE. The best MSE coming from number of estimators, a little more than 1,000, and the number of jobs being close to 25, 26. And if you are looking at R squared, then the game changes. The one that gives you the best R squared is little more, 13, 1400 estimators. So it needs more trees to get the best R squared model.
For MSE, we should look at the least, right? So I think it is correct. I mean,
Oh,
MSE
sorry.
should be least and
Okay.
R squared should be highest.
Yeah, you're right, actually. I apologize. Let me just remove this. We should be looking at this one. Sorry. Yeah. So even for this one, it is 13, 36, and 25. I guess we should be looking at this least one. Great. Great catch. Huh? So this is it. This is it. This is your MLOps, ML flow for you. You can take care of your models and the versions. They are stored here, and you keep track of all the inputs, the outputs that are there, and you do have new model registries on, and this model therefore has been saved. Right? You can promote this model to higher environments, like using this. Select a model to copy, and this is it. This is about going to staging environment, production environment, QA environment, and so on and so forth. You could do that. I won't do that, but you could go potentially promote it to higher environment. So as you can see, it gives you a dashboard to manage your models, right, and the life cycle of your ML models. Right?
And the point you asked yesterday, the source run, you can go back and check. If you see the dazzling ape, it's mentioned in the right side. No, in the same thing, no, wherever you showed just now, the previous page, it shows the source run where it came from.
Yeah, that's right. Yeah, we covered it.
Okay.
Okay, there we go. No, it just shows the exact details of that, the source run, where am I? Model. Let's go back to this, to this. So this is it. It's a little bit, you have to get used to the navigation. I'm myself just getting used to the navigation of this. This is it. And here is the source run. and this is it. So in this, it is telling you what exactly was run. Right? Model URI and etc. etc. Right? So it is giving you some extra code that you can use now to run for running this and playing with it and so forth. Right? Some environment variables. What was the which particular versions of what was used and so forth.
Asif, is this available on all the SaaS platforms?
Yes, it is. By you mean cloud platforms?
Yes, I mean cloud platforms. Say
Yeah,
your
everyone.
company. Yes.
Everyone. See, it's open source. No? So by definition, it's available everywhere. Nevertheless, Databricks would rather that you ran it on their platform, their cloud.
Thank you.
So that's their, like, if you go to the MLflow website, somewhere there should be the MLflow website. Yeah, there you go. And as you make your way through this, you'll soon realize that there's a cloud version. But Chanda will fill you in with a lot more practical details. He has been working with it for quite some time. So in the next session, he's going to take you guys through this exercise.
So Asif, with MLflow, we tried out in this example one model specifically, and then we did different runs of it.
Yes.
I assume we can run multiple models also at the same time and register using
Oh,
MLflow.
yes, yes. In fact, that's what you do. It's a dashboard. It's a platform. Generally, the real, like, your actual MLflow dashboard will contain lots of models. Some traditional models, some, transformer encoders, BERT models, some LLM causal models, right? You will have lots of parameter tuning, LoRa's, and all of that will be there. So your dashboard won't look as basic as this dashboard of ours looks. At this moment, it is given here just to give you an idea.
Ideally, in this experiments page, you will see, let us say you have done some 10 different runs, you will find all of them here. But right now, because we wanted in this demo, we took a brand new machine and where we just ran one particular model. But we can do it in our lab. No, we will do one more, and you'll see that there will be two of them showing up, and you can view them. Is that your question, Aditya?
Yeah, that was my question. And also one follow-up thing, we were creating pipelines earlier in our labs. So how do we use those pipelines along with MLflow? Will it be a part of the lab or we are going to cover theoretically today as well?
No. Pipeline is an independent topic, and this is more for dashboarding, right? There is I didn't get the connect. We are not combining these two. The pipeline is an independent thing. It is for orchestration of the whole sequencing the what you run first and what you run next. That is what the pipeline is about. This is to do experiment tracking where for a given model, let us say you're doing this kind of a hyperparameter search, you're trying to identify the metrics and find which one is the best.
Right. So I understand that part. I was wondering how the pipelines then feed this experimentation. So I'll take the example which Asif took earlier. For example, let's say the climate is changing so rapidly. So the data is changing every day. So that means that we need to create the pipelines in terms of how the data is massaged and how the data is being ingested and how we want to train the models using new data. With that said, would those pipelines set up for the preparation of the experimentation itself? How can I do the experimentation on continuous basis? That was my question.
Aditya, so here's it is. So here's the good news and the bad news. Let's start with the bad news. This is where the cracks in all of this begins to show. As a fragmentation, different people creating pipelines, different people, doing the observability platform, and people like Qflow and MLflow trying to do the whole life cycle here. in each of them, there are gaps. They're like Swiss cheese. Like MLflow, for example, is not too good at much of the strengths of pipelines. It is not meant for ad hoc jobs, right? Now, similarly, it's not good as good at model management. In observability, it is nowhere close to Arise, right? It has some things, and what people do is, because you can call MLflow programmatically, you can actually have in your pipeline an invocation of MLflow so that you can then come to the MLflow dashboard and see the results of your experiments.
Yeah.
Does that make sense? So in the
Yeah.
pipeline, you have automated it. Let's say nightly run. Yeah? So what will happen is every night you're creating new data, you're creating new features. They're going into the feature store. You're loading from the feature store, and you are now want to retrain the model. You can actually push it to MLflow programmatically,
Got
and
it.
then you can come here and see it.
And
Got
we
it.
are doing it actually. I mean, in the very first whatever pipeline that we showed, we didn't add MLflow anywhere because we
Mhm.
wanted to keep it simple. But actually, one of those, if you remember, in that pipeline, we had multiple jobs, at least in the California housing. We had an ingestion, then we had pre-processing, then we had train test split, and then we
Right.
had the model building.
Right.
So in the model building job, i- if if we add this MLflow experimentation,
Mhm.
which we didn't do last time because we didn't want to confuse, but
Mhm.
we here we are just like deep diving into that one job and adding MLflow in it. But ideally in a real world scenario, you'll have a pipeline where you'll be adding MLflow within the job.
Got it. Okay. Thank you for clarification. Yeah, that's what one my question was.
Yeah.
Thank
Okay.
you.
Nevertheless, just be aware, guys, that the whole situation is very, very fluid. Everybody is trying to do what other guy is doing. And so overlaps are coming about all the time.
Yeah. So Asif, what I have noticed is, excuse me, there are three different stacks of things are kind of evolving. One is Red Hat OpenShift and Kubernetes with the combination of either Run AI or ClearML or one of these kind of model repository platforms. So that is one path. Second path is on Kubernetes. NVIDIA has introduced this AI enterprise platform. That is where most of this stuff can be managed in a kind of a drag and drop scenario. On top of that, Run AI is coming into the picture for the overall orchestration at an enterprise scale level. But in the open source level, and that's why I was bringing up that Kubeflow, where Kubernetes and Kubeflow, to Chandra's point, once the pipeline is built, pipeline is your literally production-like scenario. At the end, you would have the model, and that model goes in here as it manages as a repository. So I just wanted to mention that because that's what I have seen from an enterprise scale perspective, that NVIDIA enterprise, and they also have this Nemo platform, and I had to experiment on that. Most of these models are coming um, out with this .Nemo extension, and I was a little bit too confused about .Nemo extension and the other regular, model serving. So hopefully you'll cover that inference part and things like that.
Yeah, we will do inference. We'll focus a lot upon ray inference, but nevertheless, we will talk about the inference on the NVIDIA platform. But I'll just put more color to what you said, guys. Run AI that Madhu mentioned is this. It's getting a lot of attention. I think NVIDIA just acquired it. And you can do many things with it. Like, for example, because there are vast banks of GPUs, it just gives you optimal utilization of the GPU. I mean, obviously, I don't see it anywhere, but the trend seems to be that NVIDIA is, in effect, trying to be the next cloud, a pure GPU cloud in some sense, an AI services cloud. They're making steps towards that. The whole Nemo platform, if you look, it's a whole set. You can just put your model as an API, deploy your model there, and then it becomes accessible as an API, just like OpenAI. You can ChatGPT, the OpenAI GPT-4, you can access using the OpenAI API. Others can access your model using this NVIDIA platform, the NeMo, and so forth. So there's a lot happening, lots of active development, and lots of things. Thanks for bringing up Run AI and NVIDIA. In our course thing, there is actually inference on Triton, and though our experience has been that, oh my goodness, it's a hell to work with sometimes. Used to be, but now it has improved apparently. In the beginning, it was so like if everything worked, it worked. If it didn't work, you would keep scratching your head. What do I do to make it work?
Apparently, it seems to be the only solution that works across all silicon at this point.
Across all silicon, what
The
work?
Intel Gaudi, the AMD GPUs and so on and so forth. So Triton.
You mean Run AI, right? You mean Run AI, not
Triton inference.
Triton is working on Gaudi now? I didn't know that.
Yeah.
Oh, I didn't know that. I thought Triton was just specific to NVIDIA.
No, it's cross. That's why they open sourced it. It's cross silicon.
Oh, okay. That's a big thing. I wasn't aware of that. Only for inference, yeah. Only for inference. So what they do is they transpile it into at least they were transpiling it into the CUDA primitives. So we used to put models in Onyx form, and it would load it and then transpile it into the CUDA form. All right, guys. So that's all I have. Achanda, would you like to say some things before we close?
No, I think we are good.
Yeah.
I think we'll cover the walkthrough in the labs, and
Sure.
also I think if there are any pending questions from the pipelines, we can take them in the labs.
That's right. Yeah.
I hope if you can try out on the other data set where we have given. I mean, we did everything on one data set. If you can try it on the other, then you are sure that you are getting it right.
Yeah. See, guys, I hope you are doing the rest of the assignment. It is no use. I mean, if you are just following it or just watching it, you won't get much out of this course. It's a very practical course. So please, how many of you tried it out with the rest of the data sets? At least some of the use cases. Anyone here? Guys, if you have not, start doing it. We can release a solution on other data sets, but it doesn't make sense. It's very easy to, almost similar to do it, but we gave you the other use cases so you would get practice. Do that and make it work on your machines. It's important, guys, to practice it. That's all I would say.